Welcome back to Cosmos Unlocked, where we unravel the universe's greatest secrets. In the previous episode, we explored the idea that the universe might be pixelated, defined by the smallest particles humanity has ever discovered. But that's not where the story ends. In this part, we dive deeper into the fundamental particles, the forces of nature, and whether we can uncover a theory that unifies everything. Get ready for a journey beyond the boundaries of knowledge. Now that we've finished discussing the smallest distances, let's move on to another idea, the smallest building blocks. Are the electrons, quarks, and other fundamental particles we've discovered truly the most basic components of the universe? It's very likely that they're not. Electrons, quarks, and all their observed properties seem to be emergent phenomena of something more fundamental. Perhaps they are the result of smaller, more basic particles or clusters of particles. The reason we think this is because every particle we've discovered so far can be placed on a table, much like the periodic table of elements. When we discussed quarks previously, we mentioned this table. If you've forgotten, you can go back and revisit it. If you're unfamiliar, you can think of it as a periodic table for quarks and leptons. The neat arrangement and the patterns in this table suggest that there might be something deeper at play behind all of it. Scientists found clues from the periodic table of elements, which showed that all elements are combinations of electrons, protons, and neutrons. Similarly, this table leads physicists to suspect that particles like quarks might be composed of even smaller particles, governed by unknown laws or principles. Regardless, the clues are there. How can we determine what might lie between electrons and quarks? We need to make various particles collide repeatedly. If a particle is composite, made of smaller particles, then these smaller particles must be bound together by some cohesive force. For example, a hydrogen atom consists of a proton and an electron held together by electromagnetic force. Similarly, a proton is made of 3 quarks bound together by the strong nuclear force. If you use energy lower than the binding energy of the subparticles to strike a composite particle, it behaves as if it is a solid particle. For example, imagine a monkey lightly tossing a baseball at your car. The ball will bounce off without damaging the car, and in the monkey's eyes, the car is a complete whole. However, if the monkey throws a rock with enough force to exceed the energy holding the car's parts together, the rock might break off a piece, revealing that the car consists of smaller parts. To determine whether electrons and quarks are made of smaller particles, one method is to collide them with increasingly higher energy. If the collision energy exceeds the binding energy holding electrons or quarks together, they would break apart, revealing their smaller components. However, we currently don't know whether electrons and quarks are made of smaller parts. Even if they are, we don't know how much energy would be required to separate them. So far, our particle accelerators do not have enough energy to discover anything smaller than electrons, quarks, or their properties. There's another method, calculation. By studying the patterns in the periodic table of fundamental particles, we may uncover underlying laws or find new particles that fit into the table. If we can identify more properties of electrons and quarks, we might infer the significance behind the patterns, gaining deeper insights into the structure of the universe. This approach would be similar to how we deduced the relationships between elements using the periodic table. These findings might ultimately tell us whether there are smaller building blocks hidden within the particles we currently know. Currently, the list of forces, once long and complex, has been reduced to 3. 1. Electroweak force, mediated by photons, W bosons, and Z bosons. 2. Strong nuclear force, mediated by gluons. 3. Gravity, theoretically mediated by gravitons, though gravitons remain a hypothesis. How much further can the number of forces be reduced? Could all these forces ultimately be different manifestations of a single force? For now, the answer is, we don't know. We've talked extensively about a theory of everything, a framework that would describe everything in the universe in the simplest and most fundamental terms. This implies that if the smallest meaningful distance exists in the universe, then the theory of everything must apply at that scale. It must account for the smallest possible volume and describe all interactions, forces, between the fundamental building blocks of the universe in a unified way. So far, we have gathered some clues and ideas about the universe's smallest distances. We also have a well-constructed framework that includes 12 fundamental particles that cannot currently be broken down further. These particles interact through three types of forces: the electroweak force, the strong nuclear force, and gravity. How far are we from a theory of everything? The answer remains unknown. However, this doesn't stop us from speculating boldly. Judging from current trends, we may eventually develop a theory that describes the universe with just one type of particle and one type of force. Such a theory might reveal the universe's smallest pixels or even prove that no such pixels exist. With such a framework, we could, in theory, peel back every layer of the universe, explaining everything with just one particle and one force. This gives us a direction to aim for. However, keep in mind that all our current theories only account for about 5% of the universe. As we mentioned in the first episode, we still don't know how to explain the remaining 95%. One major obstacle in the quest for a theory of everything is integrating gravity with quantum mechanics. This has long been a formidable challenge. Let's discuss this issue further. In modern physics, string theory is arguably the most popular and also the most controversial theory. It proposes that spacetime in the universe might have 10, 11, or even more dimensions. These dimensions are invisible because they are either curled up or extremely small. Within these dimensions are tiny strings that vibrate. The various modes of vibration allow these strings to manifest as particles we have already discovered. They might even explain particles that we have not yet observed, such as gravitons. What's more remarkable is that string theory is considered to possess mathematical beauty and theoretical elegance. It is seen as a true theory of everything because it unifies all the forces and describes the universe at its most fundamental level. However, string theory still has several serious issues. First, although it holds the promise of describing the entire universe, it has not yet fully achieved this. Its mathematical framework is still being refined, and some aspects remain incomplete before it can be considered a fully descriptive theory. Second, string theory is purely descriptive and cannot currently make any testable predictions. To clarify whether the smallest unit of the universe is a particle or a vibrating string, any theory must make predictions that can be tested. Since string theory works at the Planck scale, far beyond our current experimental capabilities, it cannot be experimentally verified. Under such circumstances, whether to believe in string theory may be less about physics and more about philosophy, mathematics, or even faith. However, in the future, more advanced experimental technologies and smarter physicists might uncover properties of the universe that align with string theory's predictions, thereby validating it. But this has not yet become a reality. The final major challenge with string theory lies in its parameters. The dynamics predicted by string theory depend on the number and shape of spacetime dimensions. These dimensions can be configured in 10 to the power of 500 different ways, an astronomically large and impractical number. Further formalization of string theory might reduce this number, but there is still a long way to go. As of now, string theory is mathematically the most elegant framework we have, and we currently have no better alternatives. However, if someone claims that string theory is the ultimate theory and has fully explained the universe, you should not believe them. In this section, we've spent a lot of time discussing the theory of everything. The most important takeaway is to dispel a common misconception: a theory of everything doesn't have much practical use for solving everyday problems. Even if it could reveal the universe's most fundamental mechanisms, it is unlikely to have much practical application. We previously described the universe as being like an onion, with layers upon layers. As you move up each layer, a phenomenon known as emergence occurs. What does emergence mean? Let me explain with an example. The television you watch is composed of countless tiny pixels. Let's assume that each pixel is a small light. Suppose you have a formula that can precisely predict the color, red, yellow, or blue, of each light at every moment. With this formula, you could accurately predict the state of every single light at the microscopic level. However, no matter how precisely you predict the lights, you still wouldn't know what program the TV is broadcasting. To determine what is playing, you'd need to step back and look, whether it's the news or the weather forecast. This phenomenon of moving from the microscopic to the macroscopic is what we call emergence. In real-world physics, when describing the motion of a bouncing ball, you can use Newtonian mechanics, which you learned in high school. By treating the ball as a single object under force, you can draw a simple parabolic trajectory and describe the situation with a single equation. Alternatively, you could use quantum field theory to model the ball at a microscopic level, tracking the 10 to the power of 25 particles that compose it and analyzing their interactions with one another and the environment. While this is theoretically valid, it is practically impossible. Mathematically, the answer would be correct, but computationally, it's unfeasible. If we had a theory that could perfectly describe the most fundamental layer of reality, we could theoretically derive all knowledge from it, from the formation of galaxies to fluid dynamics to organic chemistry. However, in practice, this is pure fantasy, and science has never operated this way. No one expects a surfer to understand string theory and calculate how many particles are in motion in a wave to help them balance on their surfboard. Likewise, no one wants a recipe written in terms of quarks and electrons. If early scientists had started their research from the most fundamental particles, we would never have made any progress. So, in essence, you can think of the search for a theory of everything as a physicist's obsession. Throughout this search, humanity has been striving not for practical applications but to uncover the deepest and most fundamental truths of the universe. Humans excel at systematically describing the world around us, from chemistry to economics to psychology. These scientific descriptions are applied to improve our lives, cure diseases, and achieve faster internet speeds. While these descriptions are not fundamental, they are still effective and practical. However, they do not provide the satisfaction of uncovering the true mechanisms behind the universe. We want to know the deepest truths, not because they can help us do something, but because we must understand why. Today, we've discussed many of the obstacles in the search for the theory of everything. Yet these challenges have not convinced us to stop searching. Each time we uncover another layer of truth, each step closer to the core of the universe's onion, we encounter new and wondrous structures that reshape our understanding of existence. Perhaps this is what truly sets humans apart from other species. That's all for today's exploration of the theory of everything. As we reflect on the universe's intricate structure, it leaves us wondering, how do small beings like us navigate and uncover its endless expanse? Stay tuned for more on Cosmos Unlocked.